Welcome to another exciting day and workshop. So far, we heard mostly about epidemic models and the spread of viruses. Today, we will hear from our social scientists about the spread of information in social networks, and we'll see how the dynamics are the same or different. So today, we will hear a lot about learning. We're going to learn about learning. The first speaker is Ilan Lobel. And I worked hard to convince him to give this talk. He said no at least twice, but it's a fantastic result, and it's going to set us up for the talk by Suraj and then Mohammed and then Anna Andrea. Please go ahead.
Thank you, Amin. It's a pleasure to be here. Yeah, Amin asked me, "Can you present this paper?" And I'm like, "That was my job market paper, and I didn't have gray hair back then." And then he was like, no, but I want this paper. I said, I have new work. He says, no, this paper. Okay, so here's the paper. So it's with people who were my advisors back at MIT back in the 2000s. And it's got published 11 years ago. And it's about learning networks. And since we're traveling back in time 10 years, I might as well start 30 years back at the beginning of this literature and give you all a little context on social learning and what are some of the methods and what do we introduce here. Okay, so the starting point of the literature is that people often copy the actions of others. And imagine like products going viral, I'm buying something because Amin bought something, and Amin bought because Sakimon buying something, right? Or you can think of meme stock trading as in like, I buy GameStop because I see everybody else buying GameStop. And economics always worries about this issue because this kind of herd behavior could lead to things like asset market bubbles, right? It could lead to inefficient allocation of resources, bad decision-making, right? We all own GameStop, but it's not worth very much, right? And the stock not being properly valued. And the classical models of this are all psychology models, behavioral models, saying that people are being kind of dumb when they do this. But there are these really two important papers from like 1992 that kickstarted this literature, saying this can emerge as an equilibrium behavior between rational agents. And I want to walk you through the example that they do, which is going to be the basis of everything we do here today. So I'm going to walk through the Bichon, Diner, Hirschleifer, and Welch, which I'm going to call BHW here. And what is the example? Imagine people are coming into town and they see two restaurants. There's a Chinese restaurant and there's an Indian restaurant, and they need to choose one to go to. And let's say that one of them is better, but no one knows which one. And there's some prior, maybe equal priors, or maybe like slightly unequal priors. Doesn't really matter here. And agents are going to have private signals indicating where they should go. And the signal is correct with 70% probability. So I'm going to discuss a little bit more about this model in terms of signals in the next slide, but just take it at face value here that everybody has an IID signal, but it's IID conditional on the state. So if the state is 1, all the signals, you got a signal saying go to this one or go to that one, and they're correct with a given probability. And again, the 70% doesn't matter here. I just want to make it concrete. And the key idea in this model is that agents observe choices of others, but not their signals, right? I know what Amin did because I can see him sitting in a restaurant, but I don't know what drove Amin to sit in the restaurant.
So what kind of states can your agents be in?
So there's going to be 2 states of the world here, which is which one is a better restaurant. And that's what I'm trying to learn. So it's one of the things we're going to simplify. For all the talk, we're only going to have 2 states of the world. This is true or false. Yeah, the agents are going to observe a signal, and they're going to observe decisions of others, which are guesses about the state.
They will have beliefs about it.
Yes. Yeah, the state, I'm going to reserve that word for the state of the world, and they're going to have beliefs about what the state of the world is. So we're going to formalize all that stuff, information sets.
But the agent doesn't have a separate state, right? Agent
has beliefs. Conditional on everything I've seen, what I think the state of the world is. What is the probability that the Chinese restaurant's better here?
No, they do have a state, right? I have the state 1 or 0, depending on whether I see signal 1 or signal 0.
There is a universal state, and you get a signal. And I'm not going to use the word state to represent your signal. So let's just in terms of terminology, the state is global, but you have local signals.
So the agents don't have a state.
So let's walk through a realization. And what's interesting about this model, it's pretty easy to see from a realization, Let's say agent 1 gets a signal saying the Chinese restaurant's better, so that agent's going to choose the Chinese restaurant. Let's say agent 2 gets the same signal, so that agent also chooses the Chinese restaurant. Now agent 3 gets a signal that says the Indian restaurant's better, but agent 3 also sees these two guys probably had signals saying Chinese. Those signals probably are 2 of those, but one is stronger than one of mine, so I should go to the Chinese despite my signal. So the next person who comes in, this person doesn't see the signal saying Indian. So the next person who comes in only sees signal saying decision saying Chinese. So even if the majority of signals are Indian, right? Even if the truth state is the Indian one's better, you've heard it on the wrong state. You've heard it on a state that might be right or might be wrong, right? And why this formulation? Because there's this classical idea in economics called wisdom of crowds that goes back to the 1700s, which is sort of like, if you want to make decisions, if you put in a lot of, and everybody has some information, if you pull it all together, you're going to do better. And the original application comes from Condorcet saying you should decide if people are guilty or innocent by jury. And why by jury? So you can assemble a bunch of signals, and therefore you get a better on average guess. And there's also in Galton's famous state fair story where he was in a state fair and he asked everybody to guess the weight of a bull, and the average guess was better than almost all guesses. So this idea that there's wisdom in the crowds, and therefore if you combine all these signals, you should be able to do better than any individual does. And the argument in the classical 1992 papers is that this kind of wisdom goes away if you're not actually combining signals directly, but you're just observing other people and trying to make guesses about it, right? And what do I mean that this wisdom goes away? It means that the probability of making a bad decision stays bounded away from 0 as n grows, right? You don't get a central limit theorem convergence. As n grows, you should be converging if you're combining signals. Since you're not combining signals, you're just learning, inferring based on actions. You don't get this, and we're going to call this failure of asymptotic learning, because we're going to care in the limit as n grows, you're not learning the truth state. The next paper that I want to jump to, which is a follow-up paper, is this econometrica paper by Smith and Sorensen, that says, okay, so let's think about the role of signals in the story here a little bit. And what Smith and Sorensen does, and this is a simplified version of their paper. So let's say there's still 2 states of the world, but now signals are drawn from 2 different distributions, F0 or F1, depending on what the true state of the world is. But they're no longer just go here, go there, but they're more complex. The information people have is more complex. And the key object here in the result is called the private belief. And what is a private belief? Is your belief that about the state given the signal. So you do a Bayesian computation here, and you say, given the signal, this is what I think is the belief the state is 1. Now, if you look at these private beliefs, you can compute what I'm going to call P under bar and P over bar. And P over bar is the worst possible belief you could have just based on your signal. And P over bar is the best possible belief you could have based on your signal. If these are bounded away from 0 and 1, I'm going to say these private beliefs are bounded, right? So the signals are not that strong. There's no signals out there that are super strong. And if they go to 0 and 1, I say the beliefs are unbounded. You'll notice that I cheated a little, and there's a case here. This could be 0 and this could be strictly less than 1, for example. I'm going to ignore that case because that's kind of like a more complicated edge case. And I'm just going to consider these 2 cases of bounded and unbounded in this talk. And the key result in Smith and Sorensen is that if private beliefs are bounded, then that story from Bixian, Hirschleifer, and Welsh holds, and the asymptotic learning fails. But if private beliefs are unbounded, if there exist strong signals out there, then asymptotic learning actually succeeds, and you actually get to full learning. So the story in Bixian falls through. And so just to make sure that we understand this idea of private belief, what does it work? You can think of the private belief being this Bayesian computation, which really, once you use the Bayes rule, it's 1 plus, and you do the ratio of densities if the distributions have densities. And if you see, like, if the ratio of densities goes from 0 to infinity, that's unbounded. And one easy example that's going to happen that has this property is if the state is either a normal distribution, if either the signals are coming from a normal with mean 0 or a normal with mean 1 with the same standard deviation, and you're trying to figure out which one it is, which normal distribution is generating the signals. And you can see that as the as the signals go this way, they become really strong signals in favor of the state is 0. And the signals go this way, they become really strong signals in favor of the state is 1. So that's one example of like what unbounded beliefs means. And so that's kind of like the state of the art results before our paper. And let me show you how Smith and Sorensen proved this, because it's a really nice argument. We're going to use some of this and we're going to contrast. So what's the argument there? This method is called the Martingale approach. I'm calling it the Martingale approach. And here's how the proof works at a high level. So defined is no, so we defined as the private belief, which is the belief based on a near signal. Now the counterpart is a social belief. What do you believe about the world based on all the decisions, but not your signal? So now, since everybody observes everything before, everybody observes all the actions before, the sequence of decisions defines a filtration. And what does that mean? That means that all the information sets are nested with each other, right? The social belief for agent N is contained in, is something that the agent N plus 1 can totally guess, right? That's what a filtration means. And more than that, the social beliefs or Martingale with respect to, this, to the filtration generated by this. And why are they a Martingale? Because if I'm agent N and I say, I think the state is 1 with probability 70%, if I guess, what do I think the next guy coming after me is going to believe about the state? My best guess is still 70%. Hence Martingale. And then you can bring in the heavy machinery from Martingale convergence. And Martingale convergence has almost all sample paths converge. That means if you take any individual sample path, it's a convergence sequence. And for it to converge, you can't converge to like 50-50. Why can't you converge to 50-50? Because if you converge to 50-50, then you get a new signal that is making you jump in your decision. That can't be a convergent sequence. That means this, if it was convergent to 50-50, private beliefs would still be bringing too much information, which would violate convergence. So convergence means these are going somewhere where they are not informative anymore. So if you have unbounded private beliefs, the only place you can converge is 0 and 1. So because otherwise you'd get a signal that would be strong enough to move you away. And once you bring in rationality, you can't converge to 100% wrong thing, and then you get full learning. And with bounded beliefs, the learning gets stuck away from 0, 1, because once you get like a belief that's say 95% correct, you can't get signals that are strong enough to move you away from there. So that's kind of the state-of-the-art approach from before our work. Now let's get to our work. So we're interested in learning over social networks, right? Because all this literature before assumes that everybody observes the actions of everybody, right? Which is obviously an unrealistic assumption. And it's also the very hard proof technique, right? Because you don't have a filtration if you don't have this. And what we want to study in this paper is can we bring these ideas and these results in social networks, social learning, to complex social networks? And what do I mean by complex social networks? First thing you want to allow is like sort of like deterministic graphs, right? The network is some sort of complicated graph. But actually, I want to go beyond that. I want to go to some sort of like complex random graphs. And why do I want to do complex random graphs? Because I want to be able to make claims about things like, oh, people only know about their local neighborhood, right? So maybe you know exactly who your neighbors are, but you only have a belief about the other people's neighborhoods, right? What is the overall social network topology, right? So you have a belief, but you don't have exact information. And this is going to allow some really interesting estimation problems to emerge. Because imagine like I observe that Sean chose action 1, and I observe that Christina chose action 0. Now I need to make a guess if Sean made that decision independent of Christina, after observing Christina, or maybe he didn't observe Christina, but both of them observed Kimon. So I need to sort of like start making these guesses, and that makes the problem a lot harder. And the decisions I observe change my belief about what the network structure is. So that's why we need to add like complex random graphs here to make the story more interesting, in my view. So now let's get to the model. Questions before I get to the model?
I have a question.
Yeah.
Of the keywords that you mentioned rings a bell. Is it then related with the so-called belief propagation method passing algorithms on locally sparse graphs?
So belief propagation is an algorithm for you to find I don't think it's all that related, right? It's like an algorithm where you do this myopic belief sharing.
Sends my beliefs. So you get the beliefs or the probabilities, whatever you get.
Yeah.
Neighbors, and then I also send my message to
Yeah.
the board. Oh yeah.
I'd love to hear your thoughts.
Okay.
Look here, thinking on the spot, I don't know of a connection, but I'd love to hear your thoughts if you think there's a connection.
Yeah, let me just add, typically for message passing, sort of the update of the message or update of the belief based on the message is a simple linear rule, but here he assumes that the agents are fully rational. And because they're fully rational, the update could be actually very sort of like they have to solve an NP-hard problem to decide what's the sort of.
Thanks for the question.
Yeah. And let me add the following comment. So I'm assuming these agents are superhuman, right? They can solve these NP-hard problems, these estimation problems, and that's on purpose. And why do I mean that's on purpose? Because before this paper, all the learning metrics paper assumed very myopic rules of behavior, right? Because the idea is like Bayesian learning networks is not a tractable problem. You don't know how to analyze because you can't solve these estimation problems. So you don't know how to do it. And the point of the paper here is you actually, even if you can't fully understand what an individual's decision, optimal decision would be, we can still make claims about the overall long-term outcomes. We can still make limit claims. That's going to be the theme of the presentation here. And it's sort of like, and I am fully aware that I'm putting a lot of rationality assumption into my agents, but that's on purpose. I'd like to understand the sort of like ideal limit. If people were rational, what would happen? Because it's a strong contrast to everything that was in the literature before. So now, state of the world. I'm going to keep it simple. Two states, equally likely. The equally likely doesn't really bite. But the two states, I mean, you need to be a little bit careful with extension because of the issues of like the bounded versus unbounded. So we're gonna keep these things as simple as we can, and the decision we're also gonna keep super simple. Everybody guesses the state. Everybody agents come in sequence and they choose 0, 1, and if they guess right, they get $1. If they guess wrong, they get 0. So everybody's incentive is just to guess what the state is. So we're keeping these things super simple as we can. Signals, we're going to follow Smith and Sorensen and say everybody has an IID private signal conditional on the state. And the signal is generated by F0 if the state is 0 and F1 if the state is 1. And this pair of distributions is what I call the signal structure. And now the social network. Here's where the innovation comes in. Each agent has a neighborhood, which is a subset of people who have acted in the past. And you can observe all the decisions for agents in your neighborhood. This neighborhood is private information. Only you know the realization. It's going to be generated according to some distribution Qn. And the Qn, the distribution, is common knowledge. And there's one important assumption that we make here, which is that these distributions are generated independently. So all the neighborhoods. So this is super general with the exception of this assumption, right? So this is like, I'm not putting any structure whatsoever on what the distributions are of neighborhoods, but I am making an independence assumption. We have a paper that I wrote with Sadler a few years after this one that would generalize this to like correlated neighborhoods, and I'll comment on that later on. But this is an important assumption here in the results. But other than that, it's like a very general network topology. And this is common knowledge. Everybody knows the stochastic process that generates the neighborhoods, but everybody only knows their own local neighborhood. So you have an information set, which is your signal, your neighborhood, and all the actions in your neighborhood. And what I'm going to call a social network, where an instance of my model is the signal structure and a network topology. And I want to understand, can I make claims about learning versus not learning in these settings? So just as an example, you can imagine that like signals come from some distribution, and there's some distribution over neighborhoods, right? Either empty or observe the last guy, observe everybody. And once you have let me just sort of like go quickly. Once you have a realization, this agent here has a signal, and this agent observes the stuff, and this agent knows and if this agent needs to guess if this person chose one independently of these or after observing these, and that makes a big difference. Yes, Divya?
Just a clarification, are the things directed or undirected to graph?
It's a directed graph because agents are going to come in order. I'm one thing that I'm not making endogenous here is the timing of your decision making. So the timing that you make a decision is exogenous. And that forces the thing to be directed, right? Because you can only observe actions that happen before you made a decision. So everybody makes a decision only once. There's another really interesting literature that came after mine, mainly by Omer Tammuz from Caltech, where he studied models where you can make a bunch of decisions over time. And Philip Strack has done some work on this too. It's really fascinating papers, but in this paper here, everybody makes one decision and they're gone. So what is the solution concept here? We're going to try to keep this as rational as possible. So a strategy is just a mapping from your information set to 0, 1. So it's a pure strategy. No need to randomize here. A strategy profile is a sequence of agent strategies. And once you choose a strategy profile, you get a probability measure over actions, right? So this defines a probability, like the decisions become a stochastic process once you define a strategy. And we're going to say that agents are playing a perfect Bayesian equilibrium if they're choosing the optimal thing given the information set, assuming everybody else is playing the same equilibrium. So very standard. So the notion of perfect Bayesian equilibrium is usually a more complicated definition in our model because everybody acts once. It's the way the structure of the model. It's pretty simple. It's just everybody is fully rational and makes the best decision given everything they know. And the question that we want to know is if for a given equilibrium, whether the decisions are convergent to the correct thing, whether the wisdom of the crowd's idea holds or not. So what are some of the things that make Bayesian learning networks hard to analyze? One is you don't have the kind of monotonicity you might want, and it might help you a lot. So look at this network here. This guy chose 0, these 3 chose 1, and this guy chose 1. Now keep all the signals constant, except for this one. Let's flip this signal here to make this guy a 1. It's perfectly plausible that this one switches from 1 to 0. This one switches in the opposite direction. Now, why can this switch in the opposite direction? Because when these guys are all choosing 1 despite seeing a 0, that's a really strong signal that the state is 1. Now, when these guys are choosing 1 because they're copying this one, that's a much weaker signal in favor of state 1. So even though you switch this from 0 to 1, this guy's social belief went in the other way. So this guy might switch from 1 to 0. So you don't get the kind of monotonicity that would be super helpful, the kind of stuff that Ali was using left and right yesterday. And now less can be more. So there's another kind of monotonicity you don't have, which is I can remove some edge and I can make this guy better off. Because it's possible that like there's too many people putting too much weight on this guy here, right? So it's not the case that like a complete network is the best one for learning. So now, any questions before I get to our approach to what do we actually do? No, okay, all right. So here's our contribution to actually solve the model. Instead of using a Martingale approach, we're going to use what I call an improvement function approach. And think of an agent n observing only one neighbor. So agent n, the neighborhood of agent n is just b. Now in equilibrium, I can make the following claim. Agent n is better off than agent b. And why can I make this claim that agent n is better off than agent b? Agent n has a very simple heuristic that agent n can use, which is copy agent b, do whatever they do. And that will give agent n the expected utility equal to this, right? Remember, I assume that the probability is equal to expected utility by putting the utility 0 and 1. Now, if agent n is choosing to disregard the action of agent b and doing something different, they must have strong information that that's a better thing to do. So they can do better. So I might be able to use this to make an argument that if you're observing agent b, you can do better than agent b. Here, this very simple argument, I just use a weak inequality. To actually get somewhere useful, I need to make this inequality strict. So
could you repeat the last part? If you observe agent B, you can do better than agent B, or you can do better than not observing?
If you observe agent B, you can do weakly better than agent B. Because you have a heuristic available to you, which is I copy agent B. And if you're choosing not to do that in equilibrium, your expected utility must be higher. And this is your expected utility of copying agent B. So this is a key idea. We're going to build on this quite a bit. So thank you for stopping me there. We would like to make this a strict inequality, right? Somehow quantify the gains of information you have over an agent you observe. And if you do, maybe we can build this, turn this into a Lyapunov function. Maybe we can use a little bit of control theory to say we can drive the system to the right place here. So that's going to be the technique that we use in this paper. So let's start with the case where you observe one person. You observe one person, I actually know how you should decide there. That case is easy to calculate. And the optimal thing to do is, if your private belief is somewhere in the middle of some two thresholds, it's like it's not a very strong private belief, I copy what I see. Right? If I don't really have a strong private signal about what the state is, I just copy what I do. But if I have a strong private signal, I ignore what agent B did and I do something else. So if I have a very strong signal, the state is 0, I choose 0. If I have a strong signal, the state is 1, I choose 1. And if I'm indifferent, if I'm kind of indifferent, I choose to copy. Yes. The lower and upper thresholds. Yeah, we have explicit. Yeah, that's going to come in this point here. A couple bullet points down the road is going to be, I can compute them. They're easy to compute based on the conditional probability of the state being correct under the state is 1 and under the state is 0. So I have closed form solutions for them.
So there is no possibility that it falls into really the lower threshold and upper threshold because it's not included, right?
Oh, I mean different. If I'm in the lower threshold, there's an equilibrium that chooses 0. There's an equilibrium.
No, because it's close to interval.
Oh, I'm saying no. I didn't put the exact thresholds in this here because there's an equilibrium that chooses this. There's an equilibrium that chooses that, right? So you're indifferent between the two options.
Thanks.
If you're right at the threshold, you're indifferent. So I'm saying that if you're not indifferent, if you're not right at the threshold, you need to choose this way. If you're at the threshold, if you're in this threshold, you can choose between this and this. And if you're at this threshold, you can choose between this and this. So there's multiple equilibrium vectors. So the argument that I was making before is that there should be a strict improvement if there's a positive chance that your decision is different than agent B's. So to get strict improvement, what do I need? I need the private signals to be unbounded. Why do I need the private signal? Why is this private signals equivalent to private signals being unbounded? I need, for any thresholds that I get, and these thresholds are strictly between 0 and 1, then I always have some probability of having a private signal above this and a probability of getting a signal below this. So if the private signals are unbounded, then I do get a strict improvement here. And these thresholds, as I was mentioning, are a function of a two-dimensional state. They're a function of the probability the state is 1, the probability agent B made the right thing given the state is 0, and the probability the agent B made the right thing given the state is 1. So given, if I have these two numbers here, and this is a fully rational model, so I can compute these things in expectation, right? I can pretend these guys are super rational computers and they can calculate these things. I can use that to determine these thresholds. So the tricky thing here is that the state space is two-dimensional, not 1. So to get a Lyapunov function, I really need a strict improvement that applies for all values, right? So all values that lead to the same probability of xb equals theta, right? Which I can simplify as this plus this equals a constant. I need a uniform gain over all of those. So that's where some of the technicality comes in. I'm going to skip the technicality, but there's like at least 10 pages in the paper on this stuff. Is actually constructing a function z, saying that you actually can get this strict improvement that is uniform. So a lot of the math is hidden under here, which is saying there exists a function z. And this function z is strictly bigger than the identity for every number below 1, such that if you observe the action of agent B, you can do strictly better than agent B by this function z. Right? This tells you like, if I observe Kimon and Kimon is 80% right, the z function say, then I can do at least 82% right. And I cannot construct something like this if the private beliefs are bounded. So this is going to be the same distinction in a way as Smith and Sorensen. It's coming from a different reason here, but it's coming the same distinction. And if you are familiar with control theory, z of alpha minus alpha is a Lyapunov function here, right? This is going to be a Lyapunov function. This means the system is going to have to go to 1. If everybody's observing one person. So here's a corollary that comes immediately from this lemma. If everybody observes the guy before them, then you get learning if and only if private beliefs are bounded, because you have a Lyapunov function if and only if private beliefs are unbounded.
Is it unique? The Lyapunov function, is it unique? And is there a standard way to construct it? Or?
There's a Lyapunov function?
Yeah. Is it
No, it's not unique. It's, I mean, we spend a bunch of pages in the paper just constructing one. All you need is to construct one.
Yeah, I know, but is it standard way to construct it? Is it there's a method to construct it, or it's trial and error, basically, just like?
No, it's sort of like I mean, the key part here is you need to like find the worst possible situation. Like, given that the probability of B equals theta, there's all these possible possibilities. You need to sort of like look at what the worst possible is and put the increase and use that as your Z. So it's kind of like doing the Bayes method. What?
It's an art.
Yeah, exactly.
No, it's like doing a lot of Bayes rules. It just comes out of like working hard on Bayes rules.
Dynamical systems. That's why I'm asking. There's no standard way to construct it.
Yeah, no. So it comes straight from the Bayes rule.
Okay.
But so it takes a little bit of work to get to the one that works.
Nice.
But then we get one, and it says here we already have a result that's new in the literature, which is if you observe just the guy before you rather than everybody before you, you get these private beliefs converge versus don't converge. But there's a very specific network. I was pitching that I want to do this in complex social networks, not when you observe the last guy, right? So now let's try to generalize this to other networks. Now, instead of agent B being a singleton in agents and neighborhood, now let's say the neighborhood contains B, but there's more people there. Then I'm going to argue the same Z function still applies. And how can I argue the same Z function still applies? I'm going to do the same thing I did before, which is I'm going to build a heuristic and say that heuristic is available, and the heuristic gives me this. And in equilibrium, you can do better than any heuristic you have, right? So if you're super rational, you can do better than any of the heuristics. So all I need to do is build a heuristic, calculate the value of the heuristic, and that serves as a benchmark for me. And the heuristic is pretty simple. Throw away all the other decisions in your neighborhood, just choose B's, and then make the optimal decision based on your signal and the decision, right? You have all these decisions there. One option you have available is toss everything away, keep one. And if you toss everything away, keep one, you get this, So in equilibrium, you need to be doing better than this. So since all I want to do, so with complex neighborhoods, once I have a bunch of agents, I have no idea how to characterize equilibrium strategies. So if everybody observes one person, I can do an exact calculation of what each person should be doing. But once you're observing two people, I don't know how to do that because the correlation could be really complicated. But I don't need to. The story in the paper is like, all I need to do is sort of like bound the quality of decisions. And if I can bound the quality of decisions, I can make claims about what happens in more general networks. So if you think through what this implies, it implies that if lines exist in the network for all agents, and this is very vague and not formally yet, but I'll formalize in the next slide. But if the notion is, if every agent can find a line backwards, then you can get learning just like before, right? You don't need the agents to be on a line. You need the lines to exist in the graph topology.
So you sort of crucially using that there does exist sort of this question. It will become calculated, but sort of. Yes, I'm very crucially using that
these agents can do better than at least these simple heuristics.
No, but
so
I mean, maybe if they did optimally, they actually wouldn't converge, and you.
They would. So that's the theorem of the paper. Under the conditions that I get learning, if they do the optimal thing, they will converge.
I think what he's saying is that if the underlying network is a Hamiltonian, maybe the derivatives for linear of the Hamiltonian to canonical cut, then I think you can improve your functions, the optimal function.
No, that's not what I'm saying. No, what I'm saying is.
You're gonna give him the mic?
Yeah, please, yeah. Yeah.
You sort of have this meta theorem that if you have any greedy strategy which actually gives you learning, then the optimal strategy, which we have no idea how to calculate, but we know exists by abstract nonsense, must also learn.
So I can't make that statement about the overall thing. The statement is about an individual agent. An agent in the network has a strategy, and if the agent can do better than that strategy, and if all I'm keeping track are these probabilities of correctness, the only thing that better decision making can do is push an individual's decision up. It's perfectly plausible. There's nothing here that disproves the following fact. If agent n does better, that could be worse for agent n plus 1. But all the bounds will still hold. So I'm not making any claims that like making one agent better off will make future agents better off. It's a little subtle here, but the argument is there is a lower bound that I can obtain here as a function of your position in the line. So let me show the line argument a little bit more formally. So suppose you have a deterministic network. This is your graph. Everybody, you trace back the longest line you can and count how many agents is I. So this guy has a line of size 5. 1, 2, 3, 4, 5. So I can, how good is the decision of agent 8 is at least z of z of z of z of z of z of the prior. And I use z 5 times because the elevate is 5. So I can bound the quality of the decisions as a function of how long the lines are.
Oh, sorry, I just returned to the same topic because the Lyapunov exponent power is indeed determined by the length of the backtracking path.
Yeah, so the bound is based on the path.
Exactly. So your bound improvement indeed is a power to the Lyapunov exponent thing is indeed depending on the path where you can kind of.
Yeah, it's not an exponent, it's a composition thing. But yeah, I apply the function, the improvement function. N times if you're at the nth position here. But now let's think about the converse. Now let's assume if this limit goes to infinity, then by the Lyapunov argument I learned, if this limit doesn't go to infinity, then lim-inf of ln is finite, which means there's a sequence, there's a subsequence here that converges to a finite number. And anybody in that subsequence can only be pointed to the first few guys. So the learning cannot happen for those guys. So this turns out to be an exact characterization for full networks. It requires a little bit of thinking to see the converse, but it follows from this. Now, what if I go to graphs? Can I expand the same idea to like random graphs? And my argument is going to be yes. The same characterization works in random graphs. I just have to be a little bit more careful with the definitions here, which is now not exactly about the lines, but I need the largest element in your neighborhood to be convergent to infinity in probability. So if the sufficient statistic here is everybody has this stochastic neighborhood, pick the largest element. I want that guy in probability to be going to infinity. So as n grows large, the largest element is always, it gets bigger than any k.
What do you mean by largest element?
The agent that acted last. So these agents act in a sequence. So if agent 100, the key sufficient statistic here to make this claim is like, if this agent 100 could observe agent 90, that's the largest one that one could observe. So I can ignore the early agents, right? Because you can imagine like the early agents don't really matter here because they didn't have a lot of signals in them. And the converse of this is that I have excessively influential agents, which is there exists an infinite number of agents who with probability bound, uniformly bound away from zero, observe only the excessively influential agent. And this notion of expanding observations is equivalent to there not existing excessively influential agents. So it's not hard to show the following result, that if the network topology does not have this condition, then no equilibrium can learn, because it's just a signal counting argument. The people who don't satisfy this limit, they're not going to have enough signals to learn as n grows. But the cool result is the other way, which is if you have unbounded private beliefs and you have expanding observations, then you do learn. Because this is the right stochastic network generalization of the notion of you have long paths. That's, I think, is the most interesting result in the paper. There's several other results that I'll discuss, but I personally, this is my favorite result in the paper. And it sort of says that if you have these unbounded private beliefs, expanding observations is the exact correct characterization of whether learning happens or not. So one thing to think about is consider the following network topology, where everybody observes agent one and the agent right before them. So most of the myopic models in the literature would tell you that this is a terrible network for learning, right? Everybody observes two decisions, right? One decision that is good, one that's not very good. And you're not going to be able, there's some confounding going on there, right? So because there's this agent one who's influencing everybody, you're going to end up somewhere bad. This does not happen in a Bayesian model. In a Bayesian model, people learn to ignore agent one. So an implicit assumption here is I know to identify who is agent one, right? So I know who I'm focusing on, who has good information. And this issue that I know who to identify really becomes key in my follow-up paper with Evan on correlated neighborhoods, because learning to identify becomes hard there. And so the way I interpret this result is that asymptotic learning is super robust if you have unbounded private beliefs. Right? Really, the networks where this fail are really like very broken networks in a way. There's no way the learning could happen just by a signal counting argument. Now, what happens if you have bounded beliefs? So this is the kind of the original setting, the BHW setting, where you have, imagine you have 2, 3, 4 signals. You have a finite number of signals. And this whole literature started that learning doesn't happen there. So now the first result that I have for here is I'm going to construct a set of networks where you do get learning. Then the way it's defined in the paper is more complicated and more general than this, but I think this is easier to understand. So imagine I definitely need expanding observations, because if I don't have this, I can rule out learning. I'm going to add two things here, and they seem a little contradictory. I'm going to add some people who see nothing and some people who see everything. And the sum, I'm going to add infinitely many of them. So the sum of these probabilities is infinite, and infinitely many of these. But notice there's a lot more of these than these, because the sum of these probabilities is infinity, but these are uniformly epsilon away. So there's a decent number of these guys in the network, and there's a very few of these in the network. So this might seem crazy. Why? How can this help? Right? I'm adding these guys with knowing who can't observe anything. I'm adding these guys who can observe everything. And I'm going to argue here that then if you have a network that has these kinds of properties, then learning always happens. So to prove this result, we're going to combine the technique in our work of expanding observations and doing these improvement paths with the technique of Martingale's. So let's walk through the argument. So uninformed agents, they act based on their signals only, right? They don't have anything else. So they're bringing in sufficient information to the network, and there's infinitely many of them. So you're going to get infinitely many signals in the network. Now the aggregators, they can learn the state. And how can they learn the state? This is kind of like, it might be tricky because they don't know exactly who is making these decisions, right? You don't know. But by seeing that people chose 1 when everybody else chose 0, you know that that's very likely somebody who had, who is an uninformed agent. And you can sort of like think of accounting. How frequently do these show up? Do these show up consistent with the state being 1, or do they show up consistent with the state being 0? So you can count how many people did the wrong thing in a way, right? Did the opposite of their previous guy. And based on that, you can sort of guess. And the proof here really relies on a Martingale argument, very similar to the old paper. And that's why I assume that everybody observes everything else. You don't need, as I mentioned, you can relax this a little, but you do need this sort of structure in there. And once these guys know enough, there's enough of them in the network, because I assume everybody has at least an epsilon probability of being one of these guys who knows exactly what the state of the world is, that the information paths from them spread to everybody else. And one thing that might be tricky is, what does it mean spread to everybody else? Don't you have infinitely many guys who don't know what the state is? I'm saying, sure, yes, but the probability that you're one of these guys goes to 0. So by assuming this thing here, I can still allow for the probability of these guys to go to 0. And if the probability of these guys wasn't going to 0, I would be violating expanding observations.
So one way to say this is to say in the unbounded private beliefs everybody has questions by now. So one way to say this is to say when you have unbounded private beliefs, some signals don't get suppressed because they're strong enough that they don't get suppressed. Here, since you have bounded private beliefs, you have these uninformed agents who don't suppress their signals because they don't see anything else.
Yeah.
And
But you
you
also
get to see those.
that's part of the answer, but the other answer is, and it's going to become more clear in the next slide. I also need some guys to be able to observe enough of them to make this work. Now let me show you the next slide where your argument fails. Because now, if I had exactly this, but now let's say that I have a constant bound M of the size of bound increments. Then I can't get learning with private beliefs, with unbounded, with bounded private beliefs. So I do need some agents that observe more and more people. So if there's one caveat to what I'm saying. So this implication here is you need aggregators for learning. There's one caveat here that I strengthen my network. I put a network assumption here. And the network assumption that I had expanding observation was this guy was going to infinity in probability. Now here I'm strengthening this, so this guy goes to infinity almost surely. So there's a stronger assumption here. And why do I need this assumption here? First of all, I don't know if I need this assumption. This is what I was able to prove. It's possible that you could get this. But the reason I use this assumption here in my proof is that since the largest guy goes to infinity almost surely, you always have one guy in your neighborhood who's very high. So you're always observing somebody who has a very strong signal. So somebody has a very strong social signal. So that means like this kind of stops people from having uninformed decisions, right? So this also stops the uninformed. Maybe it's not. So let me take it back, because when I put this assumption, I'm also stopping the uninformed people from being there, right? Because the maximum guy is converging almost surely to infinity. So this also blocks the uninformed people from existing. But there is definitely an open question here, which is if I weaken this to improbability, then this becomes expanding observations, which I know is the minimal condition for learning. Can I rule out learning here? I don't know. That's an open question. But the way I think about this is that when you have private beliefs that are bounded, you can't just sort of like look at one guy and learn from them. You kind of have to look from a large set of people and try to learn from them. So you need, in a way, there's a distinction between this sort of like improvement type learning, where I learn from one person and my signal, versus this Martingale style learning, where I'm learning from a lot of people plus my signal. And in a way, I feel the literature is sort of like missing more. You could think of other heuristics you could use to sort of like make claims about this. It's just hard because once you start putting a bunch of agents in here, and there could be a lot of information in there, but it's hard to parse how much information there is because you don't know exactly the correlation structure. It could be very complicated.
But this does not rule out what Amin was saying, right? Like, because here it seems like the uninformed agents are vanishing. Like,
yeah, here you can't have uninformed agents because everybody has a high neighbor. So the neighborhood, the maximum element in every neighborhood is converging to infinity almost surely. But yeah, there's definitely a gap in our knowledge about what happens in this case. But so the interpretation here is subject to an asterisk. My interpretation. So let me just comment on a couple of follow-up papers that I wrote with Evan Sadler on this problem. Evan was a PhD student at NYU with me, and now he's an assistant professor at Columbia of economics. And the first paper is like, let's generalize the networks so that you don't have this independence assumption. And the question is, do the results kind of hold? And the answer is not really. Is that you can get this, so there's two interesting stakes there. One is that there's a failure there that's worse than the failure of asymptotic learning. Like, because with the Martingale arguments, you always get to at least as good an information decision as if you had a very strong signal. It's possible that those strong signals are not there. And once you have correlated network, you even fail on this condition. And the issue that comes up is that this improvement becomes harder because I not only need to point to somebody who an expectation is good, I need to point to somebody that, given everything I know, is good. So I need to sort of like figure out who I want to improve from. So there's a whole machinery that we had to build for this paper to sort of like extend the improvement principle to general networks. And it's not as clean, the results, because it's very hard to characterize this notion of which agent I should be looking at, given everything I know, to try to improve on. And we also had a paper that extends this paper to if you have diverse preferences, like if people have preferences for being correct and preferences for choosing action one, and those are diverse in the network. And the argument there is sort of like the Martingale style aggregation is actually positively affected by this, because this brings more signals into here. But improvement principles actually gets hard because you're learning from one agent, and that decision is now noisier because you don't really know that the preferences of the person you're copying from. All right, so just some concluding thoughts. So the prior state of the art on this model, on this problem, was based on Martingale convergence. It's a really powerful hammer, but it requires this filtration, which makes it like far from an ideal tool for networks, because you need information sets to be nested, which is pretty unreasonable in networks. And our paper proposed an alternative approach based on this improvement heuristic. And the idea is it's an easy heuristic to characterize, and in equilibrium agents need to be doing better than this. And this gives us a lot, and it actually gives us a full characterization of what happens in the unbounded private beliefs case. And it gives some progress on the bounded beliefs case, but not a full characterization. And I just want to conclude by saying this paper is now, what, 14 years since I put it out on the web, and 11 years since it came out in the journal. But there's been a lot of brilliant work that followed up mine. I know many people here have worked on this problem. I know Amin has worked, I know Kimon has worked, I know Ali and Azarash have worked. Many people have worked on this problem and have done really interesting work. But I want to highlight two papers that I personally think are awesome. And I'm not citing all the papers. I'm just citing two papers that I think people really should know. One is by Elhanan Masel, Alan Sly, and Omer Tammuz. And it came out in Econometrica now 7 years ago. And it does a similar thing as mine papers, and like it does a pretty full characterization of what happens, but assuming that agents can act over and over and over again. And it's very hard because then agents are strategic in their decisions, because you might want to make a bad decision today to help you tomorrow, but they're able to show that the myopic one is a good approximation. It's a really beautiful, very complicated paper. I mean, the fact that these are mathematicians really comes out. And the other one is this paper by Dasarata and He that won the best paper EDC last year. And this paper does the following: instead of looking at general signal structures, it looks at Gaussian and says, once I restrict to Gaussians, I can do exact computations of how much learning you have. And you can make, like, you can say the social signal is worth 1.3 private signals. And therefore they're able to do a much more like exact analysis than I can, because Gaussian brings a lot of predictability. It's really a nice paper too. So that's it. Thank you very much.
More questions?
So I consider Gaussians unbounded. So what was there to do? I thought you sort of killed the unbounded problem. So why was
they're able to,
anything?
so a lot of papers that came out are trying to understand rates of learning. And I think one of the key papers here is that like you learn a lot from 1 or 2 generations and you learn almost nothing after. So my technique doesn't say a lot about rates. It does a lower bound on rate. That's not a very good lower bound. And this one is able to tell you exact bounds, because by going to Gaussians, they're able to, they no longer have to bound things, but they can make statements about, oh, this decision is worth that many signals.
So I was wondering if you know some other papers who have used this sort of improvement heuristic to study other sort of non-Martingale settings. So do you know if this is?
I mean, I've seen other papers using the improvement heuristic in this kind of context. Is that what you mean?
Yes.
I've come across them. I can't really tell you at the top of my head.
Yeah. Thanks.
I mean, it is one of the standard tools in the toolkit now. A lot of people have used it after my paper. I just.
Another question.
I think I might have missed something. When you went from like a known deterministic graph to the stochastic one, like I think I followed the in the deterministic graph, like you just need to find a path. But in the stochastic setting, even if there was some like path that existed with high probability, but you as an agent, when you see your neighborhood, you don't know where the path is, right? So you wouldn't know which one of the neighbors to kind of base your estimate off. And so
Yeah.
how do you handle that, or what?
So the way we handle that is really, I don't need to know the paths. All I need to do is I can use the probability you're correct as a sufficient statistic. And if I have a high probability of observing you, I have a high probability of being able to observe you. So there's like an expectation over, so the thing that I iterate over and over is like an expectation over Z. So it becomes, I definitely skip some steps there, but it is a non-trivial step. There is a non-trivial step, which is instead of just sort of like doing Z on Z on Z on Z, like on a deterministic graph you can do, you have to do this expectation there every other step. As in like, there's a high probability here that you can observe somebody high. So I can use that to bound. So that serves as a Lyapunov function.
But there's also like, I have to know the distribution of your network and your.
Yeah, so the assumption here is the distributions are common knowledge. All the distributions of all the neighborhoods are common knowledge, and you use that in your computation.
Computation of the Z's, or?
No, it doesn't show up in the computation of the Z. The Z comes from the observing one agent.
Okay.
From the update rule.
Yeah, but it shows up in the. It shows up when you apply it, right? The Lyapunov type application.
All right, very good. Thank you so much.